Welcome to solverfy.
Okay, this problem is asking us to perform synthesis for each of these reactions. Okay, so first up I have this methylphenyl ketone, and we're going to transform that into this compound right here. Okay, so when we're comparing these two, we have the presence of this single methyl group. Okay, so that's one carbon, and then we have to add two more carbons right here, 1, 2, to that specific carbon. Okay, so luckily with my methylphenyl ketone, there aren't very many options in terms of possible carbons to deprotonate, so we only have this one to deprotonate. Okay, and this is going to perform a very specific reaction, which includes a non-nucleophilic bulky base, very strong by the way, such as LDA. Okay, so the reason that we use LDA, a strong, very strong base, is because we want to avoid having a self-aldol condensation or self-aldol addition with this molecule. Okay, so we don't use something like sodium hydroxide because it's simply not strong enough. We could get a mixture of products in which we have a couple of anions and a couple of these actual molecules. Okay, so we would risk having a self-aldol condensation or addition if we had a not as strong base as LDA. Okay, so again, LDA is going to go ahead and deprotonate every single one of these molecules, which is going to result in a deprotonated alpha carbon, just like this. Okay, so that deprotonated alpha carbon is going to be considered nucleophilic, and we can go ahead and attack any electrophile that we want, essentially. Okay, and the electrophile that I want to attack is a electrophile that has two carbons, in which I can have a leaving group on that second carbon. So for example, because I want to add two carbons, I'm going to have two carbons, and then attached to this carbon, for example, I'm going to have the connection to a good leaving group, such as iodine. Okay, so this carbon nucleophile is going to attack that carbon, and when it attacks that carbon, I'm going to have to release this iodine as a leaving group, and as I do that, I'm going to form my desired product. Okay, so that's that reaction. Next up, we have this one. Okay, so first up, I noticed that I have this CH2 in parentheses with 5. So that might be a little bit confusing in terms of what's what, so I'm going to just redraw this into its corresponding compound. So I'm going to have CH3O connected to my carbon, connected to my carbonyl, connected to 1, 2, 3, 4, 5 carbons. Okay, so 1, 2, 3, 4, 5 carbons right here. Okay, and then on that fifth carbon, I'm going to have the connection to this carbonyl right here with OCH3. Okay, so that is my molecule, and we want to transform it into this cyclic structure right here. Okay, so we see that we have this 6-membered ring, and then we have the connection to this ethyl group on the side of that carbon. Okay, so let's go ahead and hypothesize what we could possibly do on this one. Okay, so because we do have these 5 carbons between each of these carbonyls, I'm going to go ahead and try to do an intramolecular Claisen condensation. So for example, if I were to react this with sodium methoxide, I would go ahead and deprotonate the most acidic hydrogen, which would either be the hydrogen associated with that carbon or the hydrogen associated with that carbon. Okay, because this molecule is symmetrical, it doesn't matter. Okay, so that is going to perform a deprotonation, in which I'll get this as my product, with a set of lone pairs on that carbon right there, with 1, 2, 3, 4, 5 carbons, and then on the fifth carbon we have the connection to my carbonyl / ester. Okay, so that is my product so far, and then this is going to perform the intramolecular Claisen condensation, in which this carbon nucleophile goes ahead and attacks this carbonyl. Okay, so I'm going to form a 1, 2, 3, 4, 5, 6-membered ring. Okay, so it's going to look like this. I'm going to have my 1, 2, 3, 4, 5, 6-membered ring. So this is going to be 1, 2, 3, 4, 5, 6, attached to carbon number 1, which is right here on my left side. I'm going to have the connection to my ester. So just like this. OCH3. Okay, carbon number 2, I just have those 2 hydrogens, so I don't have to write that out. 3, same thing. 4, same thing. 5, same thing. But then 6 is where we have the connection to my oxygen with a negative charge. So 6 has my oxygen with a negative charge. And then we also have the connection to my OCH3. Okay, just like that. Okay, so within a Claisen condensation reaction, we're going to have to move the electrons from this oxygen down to this single bond to make a double bond. And in the process of doing that, I'm going to have to move the electrons away from that carbon and onto that OCH3 as a leaving group. Okay, so this is going to be the resulting product. I'm going to have my 6-membered ring like this, in which I have my carbonyl / ester over here, OCH3, and then my other carbonyl over here. Okay, so that is my Claisen condensation, but again, we want to form this product right here. And as we can see, we don't have that. So what do I want to do instead? I want to go ahead and add something to this carbon, and I want to get rid of this group. Okay, so this is going to be similar to my acetoacetic ester synthesis, in which I basically recognize that I have my ester, I have my ketone, and this is going to undergo a acid-base reaction in which I take off the most acidic hydrogen, which is flanked between these two carbonyls. Okay, so using something like sodium methoxide, once again, sodium methoxide is going to go ahead and take off that acidic proton, just like that. So it's going to look like this, in which you have the same compound as before, 6-membered ring, carbonyl over here, and then I have my ester over here, but I have my lone pairs on this carbon. Okay, so those lone pairs can go ahead and behave as a nucleophile to attack whatever I so please. Okay, in this case, I'm going to add these two carbons to it. Okay, so those two carbons are going to be attached by the formation of an SN2 reaction. So I'm going to have CH2, CH3, connected to a good leaving group such as bromine, and then this is going to add via an SN2 reaction. Okay, so I'm going to attack that carbon with my carbon nucleophile, thereby leaving the bromine as a leaving group. Okay, so this is going to be my product, in which I have my 6-membered ring, like this. I have my ester over here, OCH3, and then again I have my 2 carbons over there, and my carbonyl over here. Okay, so now we have to go ahead and get rid of this ester group, right? We want to get rid of that entire thing. So it's going to undergo a hydrolysis reaction, which we're going to use acid, H3O+, hydronium, water, and heat. Okay, that is going to perform a hydrolysis reaction, which essentially transforms this molecule, this ester, into a carboxylic acid. So it's going to look something like this. And I'm actually running out of room, so I'm going to write it kind of small down here. Okay, so it's going to be a 6-membered ring still. I'm going to have my carboxylic acid, my 2 carbons, and then my carbonyl over there. Okay, so now we can go ahead and perform my decarboxylation reaction, which essentially gets rid of this group as CO2. And all we need to do that is use heat. Okay, and heat is going to take off this carboxylic acid as a leaving group, and we're going to have the resulting product, which is going to look like this. Okay, so that's that one. Let's move on to this second to last one. Okay, so as we can see, we have this benzaldehyde, and we're going to transform it into this molecule. Okay, so as we can see, we have the connection to this carbon, we have the connection to this carbon and this carbon. Okay, so we're adding 2 carbons to this benzaldehyde. And how do we do that? Well, first of all, we have to recognize that one way to get carbons onto a benzaldehyde is to perform a mixed condensation reaction. Okay, and that is going to be a situation in which we have this compound reacting with another carbonyl compound. Okay, specifically, it's going to be an ester. Okay, but as obviously we have this carboxylic acid, but we're going to transform that ester into a carboxylic acid. So, for example, I'm going to have the reaction of this benzaldehyde with an ester. Okay, so as we can see, we're going to add, again, 1, 2 carbons. So we're going to have something that looks like this. I'm going to have my CH3 connected to my central carbon in the carbonyl, and then over here we have the connection to my ester. So it's going to look like this, OCH3. Okay, so if I react this benzaldehyde with this ester in a basic medium, such as OCH3, I'm going to have the formation of this product, in which I have my benzaldehyde. No longer benzaldehyde, I'm going to have it look like this. Okay, so if the mechanism of that is confusing, basically all we did was we deprotonated this hydrogen off of my ester, and then we ended up with a nucleophilic carbon on that alpha carbon. Okay, and then the alpha carbon went ahead and attacked this carbonyl of my benzaldehyde. Okay, and then we undergo a couple more reactions, but basically we end up with this product. Okay, and as we can see, this product is very similar to this product, the only difference being that I have the presence of my ester, my OCH3, as opposed to my carboxylic acid. But luckily, all we need to do to fix that is undergo hydrolysis. So hydrolysis involves the reaction with H3O+, hydronium, water, and heat. Okay, so that is going to be my final reaction. Okay, next up we have the reaction of this. So we have this compound eventually becoming this compound. Okay, so let's see what we have. We have two esters, and then we have the eventual formation of this carboxylic acid. Okay, so this is going to be very similar to a malonic ester synthesis, in which we don't have technically malonic ester, but we do have something very similar. And that is because we have my two esters, and then we have this carbon flanked by two carbonyls. And those two carbonyls are going to be very instrumental towards the acidity of this proton. Okay, so using something like OCH3, my OCH3 is going to behave as a base to deprotonate this acidic hydrogen. Okay, I'm going to move the electrons onto that carbon. So the result of that is going to be this, in which I have my CH3 connected to my oxygen, connected to my carbonyl, connected to my carbon slash nucleophile, connected to my carbon slash ester. Okay, because this carbon is now considered nucleophilic, I can go ahead and attack whichever carbon I so please. Okay, so as we can see, we have this carbon, that's going to be my nucleophile, and in my product, I have that same carbon being right here. Okay, so this carbon right here corresponds to this carbon right here. So we have to consider what carbon electrophile are we going to add to this carbon nucleophile. Okay, so as apparent by the product, we have the presence of this cyclopentane. So I'm going to hypothesize just for now that we add a cyclopentane to that carbon nucleophile. So that would mean that we'd have something like this, in which we have a 5-carbon compound, and then we have a bromine right there. So this is all hypothetical. I would have a situation in which this carbon nucleophile goes ahead and attacks this carbon, resulting in the loss of this bromine. Okay, so that would result in this compound. And just for now, I'm going to draw this and this as R, because right now I'm only worried about this particular carbon. Okay, so I'm going to write down this, in which I have my R connected to my nucleophilic carbon, and then on this carbon, I have the connection to my cyclopentane. Okay, so if we compare this compound down below to my eventual product, I know that this is not going to be considered correct, because again, this carbon corresponds to this carbon, and as apparent by our hypothetical product, we do not have the direct application of this cyclopentane to this carbon, right? It's separated by a bond, whereas in our actual product, the one that we want, we just have that direct connection of that cyclopentane to this carbon. Okay, so we know that we just can't attack a cyclopentyl bromide. Okay, so we have to think of something better. Okay, so what I'm going to have instead is something different. Okay, and that something different is going to be a straight chain. Okay, so I know it might be a little bit confusing, because how can we have a straight chain that transforms into a cyclic molecule? But bear with me, because it's going to be actually quite unique, and that is going to be something like this. I'm going to have a 4-carbon compound, 1, 2, 3, 4, and on the first and fourth carbon, I'm going to be connected to bromides on each side. Okay, so this is going to be perform in an SN2 reaction, just like before, in which this carbon nucleophile attacks this carbon. Okay, and that is going to result in the loss of this bromine. Okay, so as far as our product goes, we're going to get something like this, in which we have CH3 connected to oxygen, connected to my carbonyl, connected to my former nucleophilic carbon, which is now going to be added carbons to. So 1, 2, 3, 4 carbons, and then on that fourth carbon, we have the connection to this bromine, just like that. And then on this carbon, we have the connection to my carbonyl slash ester. Okay, so that's the state that we're at right now. And as apparent by the product that I just formed, this is nothing like this. Okay, they're not even close. But that's just on the surface level, because in reality, they're actually very close, because all I need to do now is deprotonate my alpha hydrogen. Okay, and that is going to be right here. Because again, I want to form this cyclic compound. And if I were to deprotonate this hydrogen, I would end up with lone pairs on this carbon, which can go ahead and attack this compound. Okay, so it's going to be an intramolecular SN2 reaction. Okay, so let's go ahead and try that out. I'm going to have the deprotonation using OCH3, which is a relatively strong base. I'm going to get this product, in which I have my CH3 connected to my oxygen, connected to my carbonyl, connected to my rest of my chain, so OCH3 over here, and then again, I still have my 4-carbon compound. 1, 2, 3, 1, 2, 3, 4, and then on that fourth carbon we have my bromine, and then over here we have the presence of my lone pairs. Okay, so that's what I have right now, and now we can go ahead and undergo my SN2 reaction. So I'm going to move these electrons onto this carbon, so that's going to be carbon number 1, this is going to be carbon number 2, 3, 4, and 5. Okay, and after we attack that 5th carbon, we're going to have to leave that bromine as a leaving group. Okay, so the result of that should be as follows. I'll have my CH3 connected to my oxygen, connected to my carbonyl, connected to my carbon, which behaved as a nucleophile in this case, and it's going to form my cyclopentane, just like that. Okay, and again, we're going to have my ester on this side as well. Okay, so right now we have this compound over here, and we need to get to this eventual product. Okay, and all we need to do is the same reactions that we've been doing throughout this whole problem. And that is going to be first of all, hydrolysis, in which we transform both of these esters into carboxylic acids, and we're going to follow that up with a decarboxylation reaction. So first up, we're going to have H3O plus, hydronium, and water, and heat. And that's going to transform both of these esters into carboxylic acids so that we can undergo decarboxylation in the future. So I'm going to have two carboxylic acids like this, in which I have my cyclopentane over here, and the other carboxylic acid over here. Okay, and then the very last step is just getting rid of one of these carboxylic acids as a carbon dioxide, and that is going to be used with heat. Okay, so that should be the final synthesis of all of these problems.